Right. Yeah. So today we are going to discuss about a new optimization technique, and that is called as uh, gradient descent. Oh, I have to start recording. All right. Just a minute. Hello. All of you are able to hear me? Hello. All of you are able to hear me?
Yes, sir.
Okay. So we'll start with gradient descent. So let me tell you what is the background. So if anyone can help me with what we were doing in the last class, towards the end of the last class. Okay. Yeah. So can anyone help me with that part?
So we took tangents and then two tangents we took and
Yeah.
minimum.
Could you be please a little bit louder?
We took tangents A and B, and one had negative slope and one had positive slope.
No, I'm not able to hear you at all. Could you type? That would be better. Just okay. So anyway, so what I'll do is today. So suppose this is fx and this is x, right? And suppose my function is like this. Okay, so I'm assuming a function to be convex, right? I think we discussed in the last class that what are convex functions, all right? And then let me talk about the 2D aspect of this problem, okay? So how it would look like in 2D, right? Okay, so it is difficult to draw, but let me try. So suppose this is the function, and this is a x, this is a y. So what you will have basically, you will have a surface, right? Okay, something like this. Okay, so you'll have a surface. All right. So what you need to do is, if it's a convex surface, right? So its cross section would look like this, the one that I've drawn here, right? Okay, and I need to start with any arbitrary point, say here or here, any point, and my objective is to reach here. All right. So this is what I need to do. Okay, so let me introduce a new slide. Oops. Yeah. So let me do this a little bit from the context of a problem that I want to discuss. So suppose you have a regression problem. All of you understand regression? Okay. So what we do in that is that we try to, so there is a set of points, xi, yi, I is equal to 1, 2, up to say n, right? So these are the points that are given to you. I'm assuming that this xi is a single variable, right? It's not a vector. So these are the points, and this we call as the training examples. All right. Okay. So now suppose there is a function. Okay. So y is, say, it is corresponding to a function which is y is equal to fx. Suppose this is my assumption. Okay. And so what I would do is, I don't know this function basically. So what I'll do is I'll try to approximate it by another function which is, say, f star x. Okay. All right. So for every point on this, right? So if I draw it like this, and suppose this is the line that I'm trying to draw through this. So every point would have an error, right? So this is my best fit line, which is basically f star x. Okay. All right. So what I'll do is, so can you formulate the error? So what will be the error? So I'm talking about least squared error, right? So all of you know least squared errors. So formulate this as a least square error problem, which you try to minimize. Okay. So error would be what? Yeah. So suppose there are n points. So what will be the error? So I'll use a summation. Xi, I from 1 to n. I'll use a summation, and then what? Yeah. What should I write in front of the summation?
y minus
Yes,
y
think about it.
whole square.
Y
yi minus y square.
So y is what? So what is this line? This is f star x, right?
Yes.
So what should be the expression inside this?
So that depends. Is it mean square error or simple absolute mean?
No, it is least sum of squared errors. So what I want is sum of squared errors.
So it would be y minus y star whole square.
Y minus
Y star
whole squared, right? So this is the, say, actual value, right? And this is the, no.
It's
Error would be
opposite.
what? Sorry?
Yi is the actual value, right? According to the...
Yeah, yi is the actual value, yeah. And this is what is my predicted value. By using the function, y is equal to f star x, right? So I'm just using y star. So this I do it for all the points. So basically what I'm doing is this error, this error, this error, this error, this error, this error. So I'm taking the square of it and adding them up, right? So this is my error. So if you are talking about a regression problem, what you need to do is, this is your error function, and this is what you would try to minimize. When you minimize this, then only you get the best fit line, right? Okay, so with this setting, let me start with gradient descent first, and then I'll come back to this particular problem of regression. So suppose I have a surface which is okay, is a surface. Okay, so typically we use J to represent a cost function in general. So J theta 0 theta 1 is a cost, is a surface, and it is representing a cost function, and these are the two parameters. All right. So these are the two parameters that you have. Okay. So the gradient descent algorithm does what? Is that repeat until convergence. So I'll give you what we mean by this. Theta j is sine theta j minus alpha times delta by delta theta j. So this is theta, just a minute. So delta theta j and j of theta 0, comma, theta 1. Repeat until convergence, right? And there is something called as simultaneous updates. Okay? And we also need to know about this alpha. So alpha is called as the learning rate. So more about this in the coming slides. Okay. So what do you mean by simultaneous update? So let me first tell you. Okay. So simultaneous update. So what you need to do. So j can take values how much? J can be 0 and j can be 1. All right. So what we do is, so we say that temp 0 is assigned theta 0 minus alpha times delta by delta theta 0 j. And temp 1 is assigned theta 1 minus alpha times delta by delta theta 1 j. Okay. And then once you have done this, okay, then once you have done this, what you do is theta 0 is assigned temp 0 and theta 1 is assigned temp 1. So this is important. This is what is called as simultaneous updates. Okay, so what you are doing, right? So you see this. So let me, once I take an example, so you keep in mind that this is how we do it. Okay. All right. So now let me take an example. So I'll take a single variable, j theta 1, a function of single variable, and I want to minimize this for theta 1. All right. Okay. So what you do here is that you have this function j theta 1 and this is theta 1, right? So what you have is a curve like this. Okay. And so this is not properly drawn. Yeah, this is better. Okay. So now what I'll do is I'll start with some theta 1. So this is the theta 1 value which I'll start with. I'll use a different color so that you can see it nicely. Yeah. Okay, so this is the theta 1 that I am taking to begin with, and my objective is to get to the lowest point here. Okay, all right. So what I need to do, okay, once you understand it for one-dimensional case, then you can generalize it to any number of dimensions. So you see, what you do is geometrically, I'll explain this first, and then I'll formulate it. So what you do is, you at this point, right, at theta 1, you try to find the slope of the curve at theta 1. So what you are trying to do is, okay, so theta 1, will be equal to theta 1 minus alpha times delta j by delta theta 1. Okay. All right. So what does this tell you? So, and what is the slope of this tangent? This we were discussing, I think, towards the end of the last class. So what is this slope? This is tan of this angle that is being generated here by at which the tangent cuts the x-axis. And so what is this slope? Is this positive or negative? Yeah. At theta 1, what is the value, not the value, whether it is positive or negative?
Positive.
Positive, right? So this is something positive. And alpha, I am saying, is a positive number, right? Okay. So what happens to theta 1? Theta 1 increases or decreases? Yeah. Theta 1 would increase. It will
Decrease.
it will decrease, right? So it will decrease by this amount, right? Which is this. Okay. So I'll tell you how to choose a nice value for alpha. Alpha is the learning rate. So learning rate, larger learning rate means you are trying to learn too fast, and a very small learning rate means that you are trying to learn very slow. So you have to be moderate, right? So you don't typically choose a very high value for alpha, and excuse me, there are problems with high values of alpha. So typically a good value of alpha is say 0.20. Okay. So what we do is now, so what will happen is that this theta 1 will get decreased, and suppose we get here. Okay. So now again what we do is we draw a tangent to the curve at this point. So now what will happen? So this is what we get. Theta 1 is equal to theta 1 minus alpha times something which is positive, right? So theta 1 decreases, theta 1 goes down, right? Or to the left, you can say. Okay. And in the next iteration, what happens? This is iteration 1. And in iteration 2, what will happen? Theta 1 would again be theta 1 minus alpha times something again positive, because this is again a positive slope. All right. So what will happen? That this will again decrease. So you'll move still closer to this point, which I call as a theta 0. Okay. Okay. So you are again moving closer, and that you can see from here also, right? So after 2 iterations, you will get this. Alpha is constant, right? And what can you say about the derivative? So that is what is called as the gradient. So what can you say about delta j by delta theta 1 when we are moving closer and closer to theta 0, right? So you can see this angle and compare it with this angle, which this angle is smaller, right? Okay, so your slope is, so now what I do is I do the next thing. I draw a tangent at this point. Okay, so what happens to the angle? Angle becomes still smaller, right? And if the angle becomes smaller, what happens to tan theta? So tan theta will be a smaller quantity. Positive, so this is in the first iteration, this is a positive quantity which is smaller. And in the third iteration, what will happen is theta 1 will be equal to theta 1 minus alpha times positive value, which is again smaller. Again smaller, right? So what will happen? So if you see these points, so initially your step will be a bigger step, and then as you approach the minima, the step size or the improvements are going to get smaller and smaller. And this is because your slope is getting smaller and smaller. Okay? And ultimately, when you reach here, right, or very close to the minima, what will happen to the tangent? So tangent will, theoretically, what will happen is that the tangent will become parallel to the x-axis, right? And what will you have is θ1 is equal to θ1 after, sorry. So after some iterations, n, θ1 will be equal to θ1, a very small positive slope. All right? Are you getting this? So when this problem is of only one variable, then there is no concept of simultaneous updates. Okay? I mean, then you don't have to worry too much about it. So, all right? So, any questions? So, it will converge when, so the stopping condition, theoretically it will become 0, but it will not become 0. So, what will happen is that, so θ1 for some iteration n minus θ1 after iteration n minus 1, if this is smaller than some number, right? Okay, then we say we stop the algorithm. All right. So any questions on this? Yes. Any questions? So now let me take the other case. Okay, so let me use the same figure so that I'll use a different color. Okay, let me use black then now. So now, suppose my starting point is here. Okay, to the left of the solution. All right. So if I now draw a tangent, okay, at this point, so this becomes an obtuse angle, right? So what happens to the slope? So this is my, say, θ1 now. Okay. Or you can call it θ1 0, so that, yeah. So now see what is happening. θ1 0, that is the initial point, and I drawn a tangent, and if I apply the same update rule, so what is happening? θ1 1 would be equal to θ1 0 minus alpha times, which is positive, and what happens to the slope? Slope is now negative. All right. So θ1, so slope is negative, and this is alpha is positive, and there's a negative sign here. So this whole thing becomes a positive quantity, right? So that means whatever theta I started off with, it will get, I'll increase its value, and when I increase its value, if you see it on the x-axis, it will move towards the right. Okay, so the only change that will happen here is that this will become negative, this will become negative, although the magnitude will keep on going, the magnitude of the slope will be smaller and smaller as we approach theta naught. Okay, so this now becomes a negative slope. Okay, and this again, the stopping condition remains the same. So I can say that theta 1, 2 and all right. So if I come here, suppose the next stop is here. So the slope would be like this, right? And sorry, this would go here. Okay, so like this, you can see. So what is happening is you are going like this. Okay, so please tell me if have you understood this or not. Okay, so any questions? All right, so now let me, so if you don't have questions, so I'll have some questions for you now. So let me give you some situations. All right, so okay. So let me first give you, say if I start here, so how it approaches this minima, right? So it starts with a bigger step. Okay, so if I draw it by the arrows, so this arrow would be bigger, smaller, 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 smaller. So this is how it will proceed. So as you approach the solution, right, your step size would become smaller and smaller. Okay, and ultimately you will converge. All right, and please remember that you are dealing with convex functions. So where there is only one minimum, right? Okay, but if the problem is that of, okay, not this is not a good curve. So let me draw it again. Okay. Yeah. Now suppose my curve is like this, right? So what are the issues? So I'm trying to make it a little bit smoother. Okay, so suppose my starting point is say here. So where will I go? Where will I reach? So let me name these valleys 1, 2, 3, 4. There are 4 valleys. So which valley I would go?
Second one.
Second one, right? So I'll land up here. All right. But this is not the global minima. All right. So this is not the global minima. All right. So, okay. So now let me give you a situation where I'm starting from here. Or for that matter, I start from here. Okay. So what happens in these two cases, this one and this one? So this is not going to take me to the global minima, but if I start here, I'll land up here. So does
Sir, your mic is muted.
Any answers?
Sir, we couldn't hear you for a time being. So,
Oh, is it?
yes, sir. I think there was some network issue.
Oh, okay. Let me just quickly check. Are you able to see the screen on which I've drawn two figures?
Yes, sir.
Okay. So let me go to the Meet. Here it is showing fine. Okay. Are you able to hear me now?
Yes, sir. Now it's
Yes,
fine.
sir.
Okay. Okay. So what my question is, does gradient descent guarantee global minima?
No, sir.
One answer I got in the chat is yes. So the answer is, it is no. It does not guarantee a global minima if your function is like this. But if your function is like this, then yes. Okay, so if it is a convex function, then gradient descent would guarantee global minima. But if it is not a convex function, right, it is not guaranteed that you get to the global solution. All right. So now suppose you are, so I'll remove this three part. Okay. So just allow me to use the eraser. So, okay. Okay. So, right. So suppose I started off with this point. Okay. At this point here, and I landed up here in 2. So what can I do to get to the global minima? Yeah. What can I do to get to the global minima?
We add some sort of base momentum to it so that even though it gets stuck in a local minima, we can push through.
Okay. We can push it. Okay. So you're saying that we give it some momentum, right? Okay. What other things we can do? Yeah. What other things we can do? Suppose, okay. So can I say that if I restart the algorithm, okay, with a different, what do you say, different initial point, say this one here, the green one, right here. So where it will take you here, right? But if I start with any point, okay, in this range, right? Okay. All right. In this range, then I am going to get to the global solution. So there is a technique called as random restart. Okay, so what you do is once you arrive at a solution, right, and you're not sure if it is the global minima, you restart it and then run a few runs. Okay, of the algorithm, and then keep track of the minima value that you are getting and keep comparing. So if you get a better minima, you take that and keep doing this. This is also not guaranteed to give you the global minima, right? But you run the algorithm a few times with a different initial point, and then you hope that you get to a better solution than you started off with. All right. So this is what is called as the basin of attraction. Okay, so what this means is that if you by chance you come here, right, in this range, right, your x value, then you will get to the global minimum. All right, so now let me give you another situation. Say a function, so this I have treated it as a maximization problem, but that's fine. Okay, so this is where you want to reach, and this is a global maximum, right? I could have, okay, let me draw it slightly differently. Okay, just a minute. Okay, so right. Okay, so let me draw it. How do I draw it? Okay, so let me okay, so suppose this is my y, this is my x, okay, and I'm looking for the global minimum, okay, which is here, right? So now in such a case, right, gradient descent is very unlikely, even with random restart, that it will take you to the global minimum, because this area or this interval is very small. So the basin of attraction is very small as compared to the interval which takes you to the which takes you to a local minimum. All right. So in this case, for such functions, the probability of getting to the global minima is very less, right? Okay. So one more thing. So another thing that we can do is suppose you have a table. Okay. So I'll try to draw this. Suppose you have a table, and you have valleys in this, right? Some are deeper, and deeper valley means the minima, global minima, right? Okay, and some are smaller, some are still deeper, and so on, right? And you have these valleys all around. So it is like that on a table you have a kind of a structure, two-dimensional stuff, right? Two-dimensional surface which has valleys in it. All right. Okay. And suppose you have a ping pong ball, right? Okay. And your objective is to place the ping pong ball in the deepest valley, which is this one, right? So I'm just highlighting this. Okay. So you want to place the ping pong ball here, right? But your gradient descent method takes your ball, puts your ball, because you started off at your starting point was such that you landed here. All right. So now what should I do? Okay, so let me tell you that on this table, I have attached some kind of springs, right? Okay, and you can shake this table. Okay, so you can shake this table, and you can decide how strongly you want to shake it. Okay, so if you shake it, what will happen to the ping pong ball? It might come out of this valley and probably land up in this valley, right? Or for that matter, in any other valley, right? All right, depending upon how strong was your shake. All right, so this is what we do in case you get stuck in a local minima. Okay, so, and the other thing is that you would not even know that you are stuck in a local minima, right? So you have to try this. So sometimes it may happen that you are already in the global minima, at the global minima, and you are shaking it to move it out of the global minima, and maybe you land up in a local minima, right? So you have to control the shake, the amount of shake that you give to the table, so that it does not come out of the global minima. Because see, this valley is deeper, right? This valley is deeper, right? So you need more amount of shake. You need to shake it more vigorously to take it out. So you somehow adjust this threshold in such a way that you don't shake it too vigorously, or you don't shake it too mildly, right? So that if it is stuck in a local minima, it gets stuck there if you don't shake it hard enough, right? So this is what, and it is similar to what is called as a momentum thing, right? Okay, so momentum is basically that if it gets stuck here, so I'm here now. So if it gets stuck here, so it comes inside with a momentum so that it travels over this ridge and falls into this minima, which is a better minima than this, although it is still not the global minima, right? So there's a lot of randomization that happens, right? Okay, so if you start with a if you use the random restart gradient descent, right? Okay, so you may, if the basin of attraction is large enough, right, you can get to the global minima. The chances of getting to the global minima are higher, but if your basin of attraction is smaller, right, like in this case, then you might not get there. All right, so this shaking thing, so this is called as simulated annealing. Simulated annealing, right? So what this basically means, so this is a term that is coming from the physics part, right? And so it is about temperature. So if you give a metal or a glass material high temperature, the molecules in that move quite randomly, right? Okay, and quite vigorously. So you control the temperature. So all right, so simulated annealing and random restart. So these are the two things that I introduced as solutions to overcome the problem of getting stuck in the local minima. Okay, so all right, so that's, oh, I could not understand one comment. That's basin of attraction. Okay, so there's one more. We can find all possible minima, and then take. Again, you don't know. So somebody is saying that you can find all possible minima and take the minimum of that. Because you may not discover all the minima. right? Okay, so I can always give you problems. So let me just take 1 minute to close this. Suppose my function is like this. Right? Okay, so you can see here that there are so many local minima, right? That it is not possible for you to figure out all the minima. Even if they are finite, you will never be sure that you have figured out all the minima, right? So there will always be an angle of chance yeah. So there will always be a factor of chance here whenever you are doing gradient descent. All right. Okay. So any questions? Quick questions that you might have. In the next class, I'll talk about the two-dimensional version of it, right? That is J theta 0. I'll take a function which is like this, and then there I'll talk about the simultaneous update